I'm very happy that you're listening today. And to introduce myself, I want to tell a little story about myself, 10 years ago. And back then I was in Spanish class, and the next day I had to hold a presentation about Columbus. And to be honest, this was not my favorite subject, and there was not a problem. I had not much time to prepare the presentation because, of course, I had to play soccer with my friends the whole afternoon. And there was another problem. I was very slow in writing down things in Spanish. So I had the brilliant idea that I wrote a script for my presentation in my mother tongue, German, and translated it with Google Translate into Spanish. And I printed it out and just read what was there on the sheet. And to be honest, the outcome was not very good. The grammar was wrong, and the sentences, they were very hard to read, and sometimes words with multiple meanings were translated wrong. So all in all, the outcome was very disappointing. Now I would like to jump forward 10 years to today. And today I'm studying mathematics at the university in Ulm, Germany. And I'm also working as a data scientist at Infinity, where we want to explain predictions for machine learning models. So, and coincidentally, I'm also writing my master thesis about transformers. And nowadays, I use a lot of tools that help me to write things down in German. For example, you probably also all know the tool, the grammar tool that always tells you that your sentences are hard and wordy to read. And this tool also tells me every time that my sentence is written in passive voice and that I have to change it into active voice. And today, I think those tools are very helpful, with text things. And but what are the main reasons? What changed from 2012 to now? And of course, among other reasons, for example, better data availability and ever improving hardware and software. One major aspect is the development of the transformer model. And currently, I'm also writing my thesis about this. And during this half year of writing the thesis about transformer models, I learned a lot of things. And today I want to share the main learnings that I have that I found especially cool and helpful. And I'm going to try to share this learnings with you today. And I think I had three main learnings during this time. And the first one is what an encoder and decoder is. Then the attention model, and what is it about with parallelization in transformer models. And some of these insights took me a bit longer to understand, and I hope that you will understand the details faster through this talk today. Let's get started with the very basics of a transformer. So basically, the transformer architecture was developed for translating text. You give a sequence in, for example, a sequence or a sentence in English, for example, sunset at the beach. You pass it to the transformer model, which consists of an encoder and decoder, and transformer, for example, translates this sentence into Spanish, like I tried 10 years ago. Because the decoder is basically an encoder backwards, we will only have a closer look at the encoder today. And what the encoder does is it converts the input sequence into a more meaningful vector representation. And for this, we want to have an even closer look at the encoder. And the encoder basically consists of a stack of many so-called encoder layers. And the input is passed from one encoder layer to the next encoder layer. And therefore, every encoder layer consists of for example, a attention, feed-forward, normalization, and dropout layer. And here it is really important to understand that those encoder layers all have the same architecture. For example, the famous bird encoder that some of you may already heard about consists of a stack of 12 identical encoder layers with the same architecture, but they don't have the same weights in the feed-forward layer and also in the attention layer. So far, we know some basic stuff about what an encoder is, but you probably don't have that much of an idea what an attention or what is that attention thing and a feed-forward layer. And for this, we want to start at the very beginning of each model, and this is the input. And for those of you who have already worked with text data, you know that machine learning models cannot process raw text data. And for these reasons, these words, they have to be converted into integers. And in this case, vectors. And for this, we already use a very smart method to get meaningful vectors. And the words, they are converted into so-called embedding vectors, which have the good property that similar words are close together in the vector space, while words that are not that similar are further apart. And in the following example, you can see what this means. This plot shows a three-dimensional vector space with 9 vector embeddings. And for example, the vectors corresponding to cat, mouse, and dog, they share a cluster and are close together, closer, for example, to other words like squash or baseball, which are sports. And at the beginning, we already saw that the input is then passed to the attention layer. But what is that attention thing? I hope your attention doesn't already look like this. If not, I'm going to try to explain what attention is. And for this, we want to look again at this three-dimensional vector space, and we have a slight problem here. We know that in natural language, words can have different meanings depending on the context in which they are used. And for this, a single vector representation, for example, the vector representation for mouse, cannot cover every meaning. And the rough idea of attention is that it figures out in which context the word is used and to which words this specific word is attending to. And so basically, the main idea of attention is that we want to represent words as a weighted average of all elements in the sequence. And this gives us then the possibility that we do not have a fixed vector representation for words, but each word in the sequence is a combination of all the words in the sequence. For example, we want to calculate the weighted average for word 1. Given word embeddings word 1 to word n in our sequence, and we have weights that are fallen from heaven in this example, corresponding to the word 1, weight 1 to weight n. And for this, we get the weighted word 1 just by multiplying the sequence with the weights. And but how do we determine the weights? How do we determine them? So for this, we are calculating the similarity between the vector embeddings in the sequence using a similarity measure called, for example, or most of the attention things that we know, they use the dot product. And the dot product between two vectors is calculated by multiplying the vectors element-wise. And for this, for example, we have the word PyData and global and the corresponding vector representation. And then we transform the words into our vectors. And then we multiply them element-wise and taking the sum. This is basically the dot product. To show this, what this really means, I want to show you a little example. We again have these two words and the vectors, and we just multiply the vectors element-wise. So for this, we take the first element of PyData and multiply it with the first element of global, and then second element with the second element of global, and so on and so on. And then we take the sum. In this example, the dot product between the words PyData and global would be 5. But the problem of the dot product is that it will have a high score to words that are similar and a low dot product for words that are not similar. But in practice, we know that the meaning of the word is better informed by complementary words. So what does that mean? Let's consider an example for that. We have two sentences. The first sentence is, I go to the gym to train for a marathon. And the second sentence is, she took the train to Berlin. And for us humans, it's pretty clear that in the first sentence, the word train refers to the verb and probably will be good described by considering the words gym and marathon. On the other hand, in the second sentence, the word train refers to the noun and probably will be good informed by considering the word Berlin. And but how can we identify words that describe the word best in our sequence? And this is getting a bit tricky now. And for this, I want to show you how this is done in the attention module. For this, instead of taking the original embedding vectors and calculating the similarity, in the self-attention, we transform the words, for example, the word train, that we want to find the words that best describe the word train in our context. And for this, we linearly transform the vector embedding corresponding to train into a so-called query and key vector by a linear transformation into different dimensions of our vector space. And this basically magically allows the dot product to focus on different aspects of the words. As I already said, this is done by linear transformation, what is basically multiplication with numbers. As we can see here, we have a weight, a query weight and a key weight, and for this is how we calculate the query and the key vector. Because this was probably a bit fast and a bit confusing, I will repeat this procedure by showing a little example. We consider again our little sentence. She took the train to Berlin, and we transform all the words in the sequence into embedding vectors S1 to S6, and then we transform each of the embedding vectors into its corresponding query and key vectors by our linear transformation. And the goal now is that we want to determine weights that we figure out words that describe the word train in this context best. And for this, this is really important now. And for this, in this example, we only want to do this for the fourth word. In the attention model, you always do this for all the words. But this example, we just want to calculate the weights for the fourth word train. And for this, we map the query vector that corresponds to train with all the key vectors. And I want to show this with a little example. So, and mapping in this context means that we calculate the dot product, which is our similarity measure in this case. And for this, we calculate the dot product corresponding to the fourth query vector corresponding to the word train, and calculate the dot product to key vector 1, which corresponds to the word sheep, and which is, for example, 2.5. And the next, we want to calculate the dot product between the fourth query vector with the second key vector, which corresponds to the word took, and which is, for example, 1.5, and so on. I think you get the idea. And since we want to calculate weights, we normalize the dot product. Normalization means, in this case, that we want to sum the dot product or the weights we want to sum. We want to have that they sum up to 1. And the idea now is that instead of taking the vector embedding corresponding to the word train, we know that the fourth word in the sequence is better informed by taking the average or the weighted average of all the words in the sequence, taking those weights that we calculated here. And to get a better idea what this means is, I want to show you an example of the famous BERT model and the attention scores to the words in the sentences that I showed you. And oh yeah, I forgot this. Those are the weights now that we want to use for our weighted average. And for example, I brought you the attention scores, as I already told you, for our sentences. The first sentence again is, I go to the gym to train for a marathon. And the BERT model says that the word train in this case is best informed by considering the word marathon and gym. And the thickness of the lines corresponds to the attention that the word train has to all the words in the sequence. And the same for our second sentence, she took the train to Berlin. And here we can see that the word train is best informed by considering Berlin, the word Berlin and the word she. And this was pretty much one pretty cool learning that I had, that the attention module is basically a pretty clever implementation of weighted average to be able to consider the context in which a word is used in a sequence or in a document or something. And the second thing that I want to tell you is the parallelization thing, because this is also pretty cool in the transformer models that you can parallelize things when processing sequences. And for this, I also brought you a little example. So if you want to feed the sequence PyData Global into our transformer model, you pass the word PyData and global to the attention layer, and the attention layer, as we already know, magically computes some weighted average, and the output is again 2 vectors. And here we have some dependencies, and you have to pass, you have to calculate all the corresponding vectors. But after that, we can pass those vectors that is the output of the attention layer. For example, we name them set1 and set2. After that, those vectors, they can be processed by the feed-forward layer in parallel. So you don't have any dependencies, and this is also, I think, a pretty cool thing to know, because in earlier models, before the transformer architecture was developed, for example, for recurrent neural networks, this was not possible. So in recurrent neural networks, you have to process the elements of the sequence step by step. And in the transformer architecture, after the attention module, we can process those words in parallel. So this was pretty much everything I prepared for today. Thank you very much for listening, and I'm very curious about your questions.
We have a question from Ellie. Can you read it, or?
Yeah. That's a pretty good question. This is what I told you when I said that the transformation into query and key vector allows the dot product then to attend to different aspects of the words. So and basically this linear transformation into different dimensions of the vector space allows this this distinction between different semantic aspects of the words. So this is why we need the query and the key vectors. And the word, no, that's it. Thanks for the question. I hope this answered it.
There is another question.
The query and the key vectors, they are also, or the weights to get those query and the key vectors, those weights are also learned during the training of the model. So basically, you get this weight matrix from the training, and then you just multiply it. This is basically then matrix multiplication.
All right, that's awesome. We still have time for more questions. So far, there are no more questions.
So if there aren't any questions, thank you very much for having me today.
Yes, there is one final question.
Oh, there's one.
Yeah, just kidding.
Sorry. Which libraries from Python are good with transformers? Basically, Hugging Face, for example, is perfect because a lot of pre-trained transformer models are available there, and then you just can download them, and they have you can either use it with PyTorch or TensorFlow, as far as I know. So depending on which library you prefer there, they have the possibility to use it either with either one of them. So yeah, basically Hugging Face is pretty perfect for that.